So now many people know this observatory as LSST, which stands for Large Survey of Space and Large Synoptic Survey Telescope. But a few years ago, the observatory was renamed, and now it's called Rubin Observatory or Vera Rubin Observatory, to honor contributions of Vera Rubin to astronomy. So as people know, she is responsible for the first observation of the galaxy rotational curves, which eventually led to the notion of dark matter. So it's one of the most prominent actually proofs of existence of the dark matter in astrophysics. Now the LSST as an abbreviation also stayed, but now it stands for Large Survey of Space and Time, which was very convenient for the camera because LSST camera, is still LSST camera. Okay, so that actually, running a little bit ahead, that's a photograph of Vera Rubin analyzing some films with galaxies imaged in the LSST focal plane. And I'll have a better QR code for associated pages. Actually, you can go to the web and see the CCD kind of browser, so you can zoom into a almost a single pixel there. Right. So let me review a little bit the standard cosmological model. So understand, people may not have astro background here, and so according to the latest data, the universe 74% of dark energy, 22% of dark matter, and then a few percent of the normal matter, which we know. And then these numbers actually may have changed because this plot is already quite a few years old. But nothing changed over the last decade, I would say, in this understanding of the universe. So now, things were created with Big Bang, and then there was a period called inflation, which throws quantum fluctuations to the structure that started to evolve after that. So there was a period of dark ages, when the matter clamped, and then the first stars appeared about 400 million years ago. So, and the age of the universe is about 14 billion years, to set the scale. And then, things started to evolve, and the galaxies and planets formed, and we're here now after 14 billion years after the Big Bang. Now, what the observation of dark energy. So dark energy, I mean, if people are not familiar with this terminology, basically it's nothing else but terminology to describe that according to the experimental data, we see accelerated expansion of the universe, which is kind of counterintuitive. But that's, the data point to this accelerated expansion. So this graph shows expansion rate as function of time. And let's see, so let me see that. All right. So, this Big Bang happened here, and then things started to fly apart and decelerating, which is quite natural, right? So things were decelerating until 8 billion years ago, when they actually started to accelerate again. And there is a wealth of data that points in this direction, though some people are not yet convinced. Now, imagine, one of the main measurements that came to this conclusion was data from supernovae, which are sometimes, certain type of supernovae, SN1A, are called standard candles. So they produce standard signal. So if you see their brightness, you can measure it. You can measure the distance to them. And the velocity also can be determined from the redshift, and there is a Hubble law that links velocity and the distance through the Hubble constant. Now, if things are as they are predicted in the without the energy, so then they would follow this line without vacuum energy. So it's yet another kind of terminology for dark energy. And then with the dark energy, so that deviates from this line. That's basically, that's the measurement that led about a decade ago, a bit more, to a Nobel Prize, you know, with for these three gentlemen. Now, there were other indications that this may be true, so that the dark energy plays a role there through the large-scale structure. So when the galaxies start to evolve, that they attract to each other and they form so-called clusters and even larger scale structures, and that, you know, the image of the universe is shown here. So you see, and actually the way they form this large scale structure would be dependent on the dark energy and also dark matter in the universe, and that all, you know, predicted through the simulations, quite elaborate simulations, and that also predict the dark energy and dark matter as well. So what is next? So it's clearly the measurement are limited by statistics, and it's very good would be good to have new probes that you know would further prove the existence of the dark energy. So surveys they map the sky fast and deep, and there were a few surveys that actually, you know, finished their work now. Hyper Supreme Camera or DES, Dark Energy Survey, Pan-STARRS as well. So Vera Rubin Observatory would be an improvement by sometimes by orders of magnitude in the statistics for this observation. Some people say that you know, it's basically an ultimate survey, and there is no kind of good reason to go to the next generation telescope observatory, because the galaxies start to blend, and you basically don't gain in the sensitivity if you build something bigger than Vera Rubin. Okay, so just to give you a quick overview, the telescope needs to be fast, so it surveys half of the sky every 2 or 3 nights. So that's much faster than before. You get 1,000 images in 6 colors over 10 years, you know, the same patch of the sky, and see stars to the 27th magnitude after co-adding. So then, you know, the exposure will be pairs of 15-second exposure. So though, you know, now it's kind of drifting more towards one exposure, 30 seconds. And that would correspond to 10 terabytes of data every night. So the Rubin Observatory director was Steve Kahn, but since a couple of years ago, Željko Izevich replaced him as the Rubin Observatory director. So the observatory is funded by DOE, Department of Energy in the US, which is responsible for the 3 gigapixel camera, and NSF, which is responsible for the telescope on site and also the data management. Now, this is located in Chile. There is a favorite location, you know, a few telescopes are already there. It's approximately 70 kilometers from La Sirena, which also have the LSST base facility, and people basically stay there and go to the mountain, you know, to do work. Now, the telescope kind of artist view is shown here, and I'll show you real photographs in a few minutes. So it will be a 30-meter diameter dome, and you know, a lot of space for control rooms, and also to store the mirrors and other equipment. Then there's also auxiliary telescope to monitor the atmosphere nearby. And the telescope itself, you know, with the camera is inside the dome, of course, and I'll show more about this later. So that's how the rays go. So there are 3 mirrors. So the primary, secondary, tertiary mirror, and then and then the light, collected light, goes through the lenses and into the camera. The camera is not shown here. So that's some early photographs, and actually there was an early start for the mirror. So the mirror production is very slow, takes a few years, and that actually was funded by private investors. And so you see, the beginning of the mirror production photograph here. Now, to do spectroscopy, LSST camera will have 6 filters, and that's like a poor man spectroscopy, which is still useful for many things. So they go from like 350 nanometers to the age of the silicon sensitivity to 1 micron. Have traditional names as all astronomers use. Now, somebody's saying something. Now, very important, and that determines the choice of the location of the telescope. Again, this astronomic terminology. Seeing is basically blurring due to the turbulence of the atmosphere, and this place in Chile is it's one of the best places. Maybe the Hawaii is a little bit better than that, but so the seeing there, if you look at the distribution of the delivered image quality, so then the median seeing is approximately 0.65 arc seconds, which is very good. So now, how it compares, if you can do better if you go to the space, and that's the same patch of the sky imaged by Hubble telescope, which has approximately 6 times better seeing in this sense, 0.1 arc second, and so that's the same patch of the sky imaged by the Hyper Supreme camera in Hawaii, 0.5, so a bit better than LSST, right? So switch it back and forth. Yeah, that's factor of 6 in the 5 in the seeing. Okay, so now the camera will map the sky, and strategies how to do it exactly. Because there are different scientific tasks and that require basically different stars and galaxies, and that's all should be balanced, and that's like one of the proposals how to map the sky. So for example, this page here, which is not visited too often, that's our galaxy. People are not very interested to have too many stars from there, and this page is visited more often. That's to have an overlap with the northern hemisphere. Just to give you a rough idea what it is, and some patches they are visited more often. That's kind of the to accumulate better statistics there. Right. So in a single slide, LSST or Very Rubin survey will observe 4 billion galaxies and measure redshifts of them, 10 billion stars in the time domain, 1 million supernovae, which is like orders of magnitude more than available now, galaxy lenses, and also it will observe 1 million alerts per night. Right. So I'll expand a little bit on this in the following. So LSST was conceived with 4 science missions in mind. One was, I mentioned already, to study dark energy and dark matter, and there are multiple probes that will do it, and I'll talk more about this later. So another was to map the Milky Way, our galaxy, then do the inventory of the solar system. So it's basically to make catalogs of hazardous near-Earth objects or asteroids, some requirements. And then for the first time, it was to create a so-called movie of the universe. Some people say that LSST, where Rubin Observatory, it's like departure from still photography to cinematography, of the universe. because, you know, it will be possible, since the camera is so fast, it will be possible to observe things at like few hours or day scale. So all these missions needs to be done in parallel, and you know, the design that drove the design of the telescope in a big way. So there are science collaborations around you know, the observatory itself, and you know, people working at LHC can kind of build parallels with the observatory is an accelerator, and then there are detector collaborations, you know, taking data. So dark energy science collaboration that was created in more than 10 years ago. So that's photographs of one of the collaboration meetings. You know, there are more people now. It has working groups, and there are analysis working groups, and computing simulation working group, and technical working group. For a long time, I was convening actually the sense anomalies working group in this collaboration. So that's a more modern kind of structure, which also project how that fits into the analysis strategy. So there are 5 probes that people want to use to to measure dark energy clusters, large structures, large scale structure, strong lensing, supernovae, weak lensing. And there are technical groups, including sense anomalies, PSF, photometric correction, observing strategy, blending, computing. And then there are also kind of groups interfacing technical groups and science groups. So that's more or less the structure of the dark energy science collaboration now. Now let me talk a little bit more about the probes for the dark energy. So as I said, regarding the supernova, it's one of the probes. LSST will have 1,000 times larger sample of standard candles than before, and that allow not only to confirm, but also it will be enough statistics to measure uniformity of cosmic acceleration as function of direction and many other things. So that illustrates this uniformity concept. Now for the gravitational lensing, again, this cartoon for people not familiar with that. So if you have, for example, circular galaxies, and then some big mass around it, so then the light actually is lensed, and you will see a picture like that. So it will be, the galaxies, round galaxies will acquire some ellipticity in a certain way around this foreground object. Some of them will be strongly lensed, like the red one. So that's what you would observe. Of course, the galaxies are not round; they have their own shapes, and so the shapes are variable. That complicates things, and you still will have elongation of the galaxies, but then you need to disentangle, of course, the natural shape from the distorted shape, right? And that's the probe called gravitational lensing. So you need to measure shear, or the ellipticity in some sense. And that means that you need to know ellipticity of your point spread function, of your resolution function, to 0.1%. So that sets the sensitivity kind of requirement. And some people think it's needs to be even an order of magnitude better than that. Now to do real measurement, you want to use all these correlations, and you come up with, for example, binning and redshift. And then you also analyze it separately for smaller distances and larger distances, and that kind of captured in this graph here that shows L, which is effectively the scale, so large scale, smaller scale, and the correlations due to the fact that this distortion is caused by the same object. And people simulate it and extract information in an optimal way from these measurements. Now, I already mentioned that the PSF plays a big role there, because if for some reason, if your resolution function is biased, you may end up with some correlation that, not due to the effect, but just due to the instrumentation. And And that, that will be subject of some studies that I'll describe in a few minutes. So another probe for the dark energy and dark matter is so-called baryonic acoustic oscillations. So those are frozen imprints of pressure waves that move through the early universe, and people call them standard ruler. So they are, they allow to measure intergalactic distances as well, and have sensitivity to the dark energy and dark matter. So all these probes, 5 probes, they can be combined. Again, people are writing software to do the combination in an optimal way. So that's one of the examples. One of the predictions, 2 main parameters of the standard cosmological model, W naught and WA. So the bottom line there is that, with the final data set, Rubin Observatory will have 100 times better discriminatory power to distinguish between different cosmological models. Now, the variable universe, the camera will be fast and can probe things which was not possible before. So at the time scale of hours, basically. And so regarding the near-Earth asteroids, so the requirement coming from NASA, basically, and from the government as well, to protect the Earth from rogue asteroids, you need to have 90% efficiency, 90% efficiency or completeness in that terminology, for objects with magnitude of 22, right? So magnitude 22 is 150 meter asteroid. So that's, the impact would be pretty dramatic, and 24 is 50 meters, etc. So currently only 22% of near-Earth asteroids, of similar size are known. So the Whale SST, complies with requirements for these four directions. What it needs to measure is large area times field of view, right? So it's sometimes called attendu, it's a French word. So to get more area, build a large camera, and to get high field of view, favor designs with shorter focal lengths and reasonable off-axis image quality. And the key to that is fast and low noise CCDs. So that's comparison of main parameters for different cameras built in the last couple of decades. So SST is highlighted in red. So regarding the pixel count at factor of 3, more than the closest camera, so 3.1 gigapixels, 189 CCDs. So you can see the focal plane here, and this object is the moon, right? So that gives you kind of the angular coverage of the camera. So it's about 3 degrees. Moon is half a degree. So then the focal ratio, the readout time is also much faster than others, despite the number of pixels. 2 seconds, that's the requirement. And decam, for example, it's 17 seconds. So the data rate, of course, it's a product of these 2 things. So it's 1 terabyte per hour. Also very impressive. Yeah, so here also this mention here that LSST camera has, it's the only one large mosaic camera in telescopes with specialized ASIC readout. So for all other cameras, you take the signal out with a cable. So that shows the camera and the focal plane. So I'll talk more about the the modules in the focal plane, but the camera itself, again, you'll see photographs. It's probably better to tell more about the camera looking at the photographs. So the focal plane has 21 raft. So that's the terminal science raft with integrated electronics. And each raft has 9 CCDs. So it's like a module for the camera. So the CCDs, to meet the noise requirement, need to work at minus 100 degrees Celsius. And so the camera, CCDs and also electronics, they must be cooled. Most people know that, but charge-coupled devices, that's the way they work. So basically, you shift manipulating by the electrodes voltages, as shown here. You can move the charge in collected charge in silicon sideways and then read it out. All right, so then to meet the 2-second readout time spec, the CCD is segmented into 16 sections. So there are 16 amplifiers, and 16 amplifiers, and for 16 megapixel CCD, so 1 megapixel per amplifier. The noise spec is 8 electrons, which is very low, and that's based on the anticipated sky noise. Pixel readout rate, it's derived from this 2-second full readout time. Pixels are 10 by 10 micron, and silicon thickness is 100 micron. So that 100 micron thickness is not usual for CCDs. And that was done to have enhanced sensitivity in infrared, right? So in so-called Y and Z band. So that corresponding to the wavelengths, let's say from 800 to 1,000 nanometers. It also has anti-reflective coating because otherwise silicon reflects about 35%. So that's the quantum efficiency of the CCD. So it's within the range. It's not too far from 100%, which again is very good but quite typical for backside illuminated CCDs. Photographs, we use CCDs from two vendors. So one is E2V, that's a British company, and so that's the left one, and another one is ITL. It's like American/Canadian company, and so they had a different outlook, but all mechanical interfaces were exactly the same. At the end, there was a competition between two companies, and at the end, LSST decided to use actually both types to meet, to have enough production rate. This is a photograph of the E2V CCDs, and so basically you see that how everything is mounted there, and everything should be, to a few micron precision, because otherwise you will not meet the this alignment specs. This zoom-in photograph shows a gap between two CCDs, so it's only a quarter of a millimeter, sorry, 250 micron. And you also see the bond wires, for example, that's how the sensor is connected to the outside world. This is structure of the rough tau model, or RTM. There are 9 CCDs there at -100 degrees. And then there are pigtails of cables that connect them to the raft electronic boards and, and all power infrastructure and also cooling infrastructure. BNL was responsible for production of the science rafts, and that's where I spent a few years of my life in this clean room, building and testing this module. So that was a major enterprise, and we had a dedicated clean room where we tested all SST sensors and assembled and produced and tested also all science raft, and that was from 16 to 19. Photograph of the raft is shown here. So the CCDs are here, and you see the cables, flex cables going to the board. That's the view of the CCDs. 9 CCDs, one of the first rafts built at BNL, and that's like a news release after we finished and sent the last raft to Slack. So that's in the front. That's a cryostat used to test the rafts. Now, Michael's group played a big role in this enterprise, and we had a constant flow of visitors working both in the clean room, and later when we finished the clean room operations, they also helped us with the CCD characterizations and other things. And Piotr Kubanik, actually, many must know him. He went on, and he is now in Tucson, actually working for the Rubin Observatory full time. So all rafts were sent to SLAC, and there in 2020, they assembled the focal, just before COVID, they assembled the focal plane. So that's also a very delicate operation, because as I showed, the gaps between the rafts is only 1/4 millimeter, right? So that should be a very very delicate operation. In this photograph, you can also see so-called corner rafts. So this object here, it has only 3 CCDs, and they're specialized. So these two can be read out faster. So they will be used for guiding. And this one, you see 2 displaced pieces of this CCD that is used for the wavefront sensing, to compensate for the orientation of the telescope. So this is full focal plane, which was assembled in August 2020, and some images taken with this, including the Vera Rubin image that I showed before. Okay, so now in this photograph, you see the focal plane already integrated in the full camera. So here you can actually see that there are 189 CCDs here, not counting the corner CCDs, and you see that they have different color. So that because we used CCDs from 2 vendors, and that had a little bit different quantum efficiency. And also that means that they reflected light a little bit differently, and that's why they had different color here. But you can clearly see the middle one is E2V, which had lower noise and a little bit better performance. But the outside CCDs are mostly ITL. Now in this photograph, you see a filter, one of the filters already installed, and if I will be able, I'll show a video actually of the filter operation. So you see how the filter kind of comes from the top, and now it's a certain filter, so it reflects most of light. So that's why I'll do it again. Oh, no, wait. Okay, that's why you see a reflection of all these people, with the cameras taking these videos. Right, so that's the camera from the other side, and that's Yusuke, postdoc at SLAC after sleepless nights. So that integrates a lot of infrastructure, engineering infrastructure, and all electrical connection, all cooling connections are there. So we had to actually kind of modify the cooling system for the camera because the first version didn't quite work. So that's was done a couple of years ago now, and the new one is working very successfully. And that's people at SLAC, a similar amount of people, maybe even more than at BNL involved in this work. All right, so let me now spend maybe 5-10 minutes talking about the sense anomalies working group. So I spent actually 7 years convening this group in DESC. So the problem, a difficulty, it's not really a problem, but a specialty of LSST CCDs is that the thickness is 100 micron and the pixel size is 10 by 10 micron. So you can compare them to skyscrapers, right? And that means that actually that actually electrostatic fields play a big role there. Similarly, what people of older generation may think about drift chambers, for example, for as gases detectors. So that's kind of similar. So electrostatics plays a role there. And that's a complication if you need to know ellipticity of your point spread function to good precision. So an example is, for example, astrometric distortions when if you're close to the edge of the sensor and has some electrodes there, so that distorts the field, and you have some lateral field, and then your ionization, instead of drifting straight like here to your pixels, turns, and so you have a bias, astrometric bias because of that. And we spent a lot of time studying that. For example, you can step your laser signal to the edge and then see how your ellipticity, for example, of this spot changes as here. So that of course that can be measured and corrected. So another very important effect, probably even more important than this edge effect, is PSF, point spread function intensity dependence. So there, as you accumulate electrons under in your pixels, for example, this is an image of a star. As it grows, it starts to repel the incoming electrons, right? So instead of going straight, the electron may go left or right. So that widens actually the PSF as function of the intensity. This effect is called brighter theta. So brighter stars are theta. And again, we created a Poisson simulator and studied that. So basically a way to describe it, that pixels that receive charge shrink, right? So effectively they collect less light so that, they have less area. Then, of course, the difficulty is that so you can study that through so-called pixel correlations. So the Poisson solver actually predicted that the effect will be a little bit different in X and Y, which is quite natural because the CCDs read out charge along the columns. So the structure of the columns is different than the structure of the rows. And indeed, this sigma is different for X and Y. And that's why you also will have ellipticity associated with this effect, which is very dangerous. As I said, we want to know ellipticity to very good precision, 10 to the minus 3 or even 10 to the minus 4. Right, so that's a study by Tony Tyson, who argued that actually the ellipticity need to be known to 10 to the minus 4. Right, so another sense effect are so-called tree rings due to the variation of the conductivity of silicon. You end up something like in the trees. So when you grow ingot, as it grows, the resistivity can be varied. So when you deplete the silicon to collect the charge, you end up with some built-in fields, lateral fields in silicon, and that cause both the intensity variation and astrometric variation. That again has been studied, by many people. So one of them is Sergey. So he proposed a new technique to measure the period, so-called periodogram, and that it was a quite subtle effect that actually the period of the tree rings depend on the radius of the tree ring. People had optical simulators and projected images of spots to study PSF. So that's UC Davis had a setup like that to project images like that and study the edge effect, for example, and other kind of subtle effects in the sensors. At BNL, we had a fringe projector, which was a Michelson interferometer to generate sinusoidal variation of intensity. So that shows. And that, again, it was used to study brighter theta effect, which behaves a little bit different there, presumably easier to study. And that's an image of the fringes in CCDs there. We used cosmics to, to study CCDs, and so that was used, for example, to measure gain and compare it with the gain, from the iron 55 source. So that's X-rays. Something that can be used actually in situ. So it's not clear that will be used, but that was a nice way to, to study CCDs. We also recently published a paper on so-called fat cosmics. So it was kind of, the interest was generated by hypersupreme camera data when they started to notice so-called fat tracks, which are, much more ionization and wider than just standard muon tracks. And, we try to argue that actually these tracks belong to protons. So when the cosmic rays come, from the at high altitude, they start to interact with the atmosphere. So those are mostly protons, and then they shower, create pions, and pions decay to muons. So muons is mostly what you see at the surface. But then if your telescope is high enough, some fraction of the protons manage to penetrate and do not interact. And they actually slower, and you have, you have 1 over beta squared dependence, Beta-Bloch formula that creates a lot of ionization. And then you have something similar to brighter theta, so this charge repels, and that's why they're wider. So that was our conclusion. All right, and we observed that data from different altitudes, like from Hawaii, from Chile, and at the sea level, they have different fractions which are in agreement with the predictions. We studied fringing with monocams. So 1 year we took a raft to Nové Observatory in Flagstaff, and actually Piotr Kubanek was part of these operations. And we took Y filter, which is the like the most infrared filter. So the absorption, there are OH radical absorption lines there, so there is a lot of structures there. And also, since the light penetrates basically through the thickness of silicon, there are also reflections and interference, and there are so-called fringes in the images there. So what we've done, we took these images, in certain patch of the sky, the same patch of the sky at different times, and then compared them, subtracted, normalized them to one of them, to this one, and we, did see variation, which is not a, very good thing. So it means that we need to calibrate it out in the data. You can't assume it's constant. And that's because intensity of these OH lines changes actually, and different lines have different intensity during this time. So we then went to the lab, and where we can project light of certain wavelengths to the sensors, and then we concluded actually that that this effect is due to only 2 OH lines at these wavelengths, and you can reproduce the sky fringes with the with the lab data. All right, so there were a number of conferences. We started them as PACCD, Precision Astronomy and CCDs, but last 2 times they were renamed to ISPA, Imaging Sensors for Precision Astronomy. So last one actually, I chaired the first 4, the organizing committee, but the last one was at SLAC a few weeks ago. Now let me spend a few minutes talking about full camera testing. So a lot of this testing and kind of ideas, what to measure, how to measure, came from our studies of the sensors, of course, which we've done for a decade before for the real camera. So there was a number of like a variety of different instruments, different projectors to study the CCDs in the full camera, like flat projector, spot projector, crosstalk projector, and then wide beam projector. That's also was used, and you see people kind of setting up these things, and more hardware related to these projectors. So that's like a summary result, for example, of readout noise. So you see that color here corresponds to the color scheme corresponds to the readout noise, and I think that's 10 electrons. So you see that in the center, the E2V CCDs, they have a little bit better performance, than ITL CCDs. And the corner rafts, normally, the sensors were selected there with not very good performance, but, they're used only for guiding, so it doesn't really matter. So that's like an integrated curve, shows the percentage of pixels with certain noise. That's of 6 electron at 50% has, better than 6 electron. So that's a photon transfer curve. So it's a standard way to measure performance of the CCD when you send a signal and accumulate n photons in a pixel. So then this n fluctuates poissonically, a square root of n. So you can actually then relate the variation, square of variation actually, and the signal should be linear, just one. If you express everything in number of electrons. And then at high signal, you start to have saturation. At low signal, you have influence of the noise. But then using this, you can extract the gain. So that's the standard way to measure the gain. So that's the gain of CCD that's shown here. Again, you see a difference between two types of the CCDs. All right. Now, we of course, we also observed features in flat images. I already mentioned 3 rings, and there also were some laser annealing pattern in the blue for E2V CCDs and coffee stains, so some chemical for the ITL sensors. Okay, so now it's time for photographs. So that's how LSST site looked in 2013. So basically it was chosen, and then the construction started in a couple of years after that. There was a lot of research studies done where exactly to have it very stable. Then that's how it looks actually during the last year when the dome and the observatory construction was completed. So that's the Oxtel dome for the auxiliary telescope for the atmosphere monitoring. Now that's the camera mechanics, not the camera, but the telescope mechanics sitting inside the dome. So you can see the opening here, and that's very kind of skewed view because of the wide angle camera. But then, all this rotation of the dome and, mechanical adjustment, etc. So that's took time because the telescope itself is very agile, so it moves fast, right? And you really want it to move smoothly. So that took time actually to prepare all this. We also produced ComCam, so it's just a single raft, but everything around it mimics the camera in terms of weight and cooling systems, etc. So that was used. That's in Chile for two years, and is used to commission basically the mechanics and the telescope. Though it hasn't seen yet the light, right? So there is a raft there, but it's not used for observations yet. Now, so that's how the LST site looked in 2017, and that's I just captured a photograph of what happened last week. So last week, so this is the primary and tertiary mirror. Remember that primary and tertiary mirror, they're in a single piece of glass. So its diameter of this is approximately 8 meters, and produced in University of Arizona in Tucson. So the blue is not the color of the mirror; it's just some protective layer there. I don't know why this is closed, but what's happening now? So this mirror is being mounted on on the telescope basically. So you see that it's supported by this rubber and so some supports. Then it's lowered to to the base, and you see also kind of these dark dots are the active optics element that will help to align the mirror when it's installed. All right, so it's happening now. So then just a few words about data processing. So that shows a typical image. It's a simulated image, but that's what, how the data will look like. So that represents like 10 to the minus 9, so just 1 out of a billion images. It's a single sensor, a single 15-second exposure. So it's a lot of information. Now, the purpose of image processing, just in very general terms, is you measure actual sky in your CCDs. So you have fuzzy, distorted, warped, noisy, vignetted image with cosmic rays, diffraction spikes, and something else. And then it goes through your image processing where you remove all these effects. So it's called signature removal. And you have artifact suppressed processed image, right, with certain requirements how your algorithm should perform. Now, again, the ultimate LST deliverable, to the public is not, of course, the telescope, not the camera, but the final science-ready data products like the catalogs. And the amount of data is quite humongous. So the camera is 3 gigapixel. So one raw image actually is already 6 gigabytes. And it will be of the order of 10 to 20 terabytes per night. So over past 10 years, it will be 100 petabytes of data, and again, 15 terabytes every night, which is order of magnitude more than kind of the previous surveys. Also, another thing that that makes it a little bit similar to particle detector. Again, trying to give parallels for people working, for CERN at LHC. So you need a trigger system, right? So will be like 100,000 to 1 million alerts. So when you observe something variable, right, and that would, that's one of the purposes of the LSST, to study the variable sky. So you actually need to provide this information. And this packet that should be available 1 minute, 60 seconds after the shutter closes. And so you provide it to, to the, what they call it, you provide it to the brokers, and they distribute it, to other telescopes, for example, to follow up the, these events. So that's the whole kind of different story how to do that. Okay, so SLAC will be hosting Rubin US data facility, and there is a facility also in Europe and in France of similar size and performance. So just a single mention of LSST simulations. So that what was developed by people in Purdue, John Peterson and others. So that's you can basically simulate all optical effects in the CCDs, and was very necessary during the preparation, so you can actually start tuning your algorithms before the data arrives. Okay, so what is the future, right? So that's the latest schedule. As it is, and so the dome will be complete by the end of this year in December, so fully complete. And the camera, I believe, today has a review at SLAC regarding the shipping review. So it will be shipped to Chile in a couple of months, and then by fall will be tested and then installed at the telescope. So the February 25 is when the camera is ready to the first photon. And then in a couple of months, there will be first images with the camera, and in August 25, first operations as planned now. So data will be public in 2 more years after that. So that's the plan now. Of course, if you would look at this plan 1 or 2 years ago, it would be quite different. And there were delays, mostly due to the COVID, because everything stopped basically for like more than a year, but there were other things, like the cooling system, for example. Okay, so now, let me show again this image of the focal plane. So if you go to QR code, so you end up at the CCD viewer webpage at Slack. That maybe too soon, I'm not sure. That will allow you to zoom in actually to almost to a pixel level in this image. And that's again, that's another QR code for a website where Vera Rubin Observatory keep the image gallery, so that is updated weekly. So you can look at that as well. Okay, and that's my summary. Basically, so Rubin is happening. First light in about a year. First science data again by the end of next year. Thank you.
Hello. Yeah, thank you, Andrei. So thank you very much for getting us up to speed with Very Rubin Observatory now, and we are looking forward definitely for the further development there, and hopefully the time schedule that you have presented will not shift. But I believe now it's everything on track, and we can hope that we will really have this first light in early next year. Maybe there are some questions. I believe we still have a few minutes for some questions, if there are any.
Yeah, we should also check the Zoom. Somebody could check.
I will go and check the Zoom. But if there are questions here in the audience, then
I'll hang around. Also, if people have questions, I'll have another coffee. I still have.
Yeah. So of course, this is another possibility, and let me see if there is anything in the Zoom. I don't think so, actually. No. Okay, so there are some questions.
Thank you for a nice overview of the whole project. I didn't know about it prior. So maybe my question would be too stupid. You've shown that all the data which are going to be collected will be distributed into some work groups that would analyze different scopes of their researches. And is there the group from the Institute of Physics is participating in what particular research?
So this is probably for me rather than for Andrei. So we have now switched into these science collaborations. So mostly we are active in preparations of these so-called brokers, which will be like clever programs that are selecting the transient objects. So this is what mostly Sergei Karpov is doing. Then we have Ivana Ebrova, and she's involved in the research of galaxies and special type of galaxies, and she can tell definitely much more than I can about this particular topic. And then we are still also active in so-called dark energy science collaboration, which deals with one of these main goals of the whole project, and this is determining the nature of the dark energy in the universe.
Okay, I would like to ask why the different manufacturers were used for half of the chips and another. It was because of the limited supply, or is there some physical reason behind this?
Yeah, my take on it is that the design of CCDs was very difficult, right? So the specs for the CCDs were very difficult, and that in the first place why we decided to go to two companies to produce the CCDs, and there was like a competition, prototypes ordered from both companies, etc. Then at some point, they performed reasonably well, both of them, and they. At some point, there was a schedule risk that, that if you use one one company, you would not meet the, the schedule requirements, and then it was a difficult decision taken, by the management to use CCDs of both types, right? So it was, maybe quite a bit of politics involved. Some people from the kind of measurement point of view, some people view it as a disadvantage, some people view it as advantage. For example, if you have CCDs of two types, you can, divide your samples and see, study systematics, for example, even on your science observables. If you measure it in one type of CCD or another type of CCD, if they're different, there is something wrong with your signature, of course, and with your calibration procedures. But two types of CCD, that's some complication.
Okay, thank you. Any other question? Yeah, over there. Please wait for the microphone.
Thank you for your report. What about meteor observatory in Very Rubin Observatory? Observation, meteor observation. Meteors.
Meteor observations. Yeah.
So what?
Microphone.
I don't know much. I don't know much about meteors, but what we will observe very well is the Starlink satellites, which will actually, there are many of them. They appear as bright kind of traces in the CCDs, and actually, is a is a reason for concern. And Tony Tyson even talked to Musk about the satellites, complaining about that too many of them, and that actually had some effect in the sense that they paint now the satellites in black, right? So they reflect less, but they're still visible. And actually, it's funny. Tony was telling about Elon Musk's first reaction about that, and he told, "Oh, why don't we launch LSST to space? Then you don't have this problem." Okay. All right. I'm not sure I answered the question. But,
yeah, concerning meteors, I don't know. Yes. So of course they will be detected just by chance, but they will be probably analyzed just as a noise and taken away. But maybe I'm mistaken. And for example, Sergey knows more, but I don't think that this is like
in terms of noise, they're probably the cosmic rays probably would happen more often as a background than meteors.
Yeah. So of course, LSST, as Andrei told you, will be observing many asteroids in the solar system. So this is definitely one of the key topics. But as far as I know, I never heard about meteoric observations. Okay, thank you very much. Maybe last question, if there is any. Okay, so over there, if someone can hand over the microphone, thank you.
Maybe I missed something. Did you mention about adaptive optics?
Yeah, there is no adaptive optics for.
So why?
There is active optics, right? There is this, which is a bit different purpose, right? So the active optics is basically, the primary mirror. When I was showing photograph, yeah. So when I was showing the photograph, yeah. So this kind of black dots here. So that's elements of active optics. So when you move the mirror, so it deforms. And so to keep it basically in focus and in the optimal position, so you have these things, pushing the mirror to adjust the surface, in an optimal way. So but that's active optics, right? So it's not something that compensates for the atmosphere. So the compensation for the atmosphere would be adaptive optics, but that's too difficult to do, right? So
it is the reason that there is no adaptive optics because it is complicated, or?
Because you need for adaptive optics, you need to read out at the kilohertz level, right? And
the problem is also with the very wide field of view. Yeah. So if you have like different telescopes, the ESA, you have very narrow field of view, but per these 10 square degrees, you actually have different atmospheric phenomena. Yeah, so you will have to have different this adaptive optics in different parts of the camera, and that's probably not worth of it.
Okay, thank you.
Okay, so many thanks for. Oh, okay, okay. The very last question.
Yeah, I will just react to this. Using the active optics, you are looking on the sky immediately, or do you use some laser system for making the alignment?
No, you use the stars.
The stars are bright enough for doing this.
Mm-hmm.
Okay, thank you.
Okay, thank you very much. Thank you to all of you for coming today. Many thanks to Andrei for being here with us and informing us about the latest developments with Very Rubin Observatory. So, and that's all for today, and have a nice afternoon and rest of the day.
Thanks for coming.
Thank you.
All right, so it's